So we want to use a graph to determine the domain and the range. Rather than finding it algebraically, we want to take it by looking straight at the picture. So this being the graph of f here, we want to ask ourselves which x values were acceptable to choose to get this graph. So we've chosen x values and been given y values through the function. Which x values were we allowed to choose? Well, let's use sweeping method. So we're going to start on this end. We're going to start toward negative infinity and see, does the graph go to negative infinity? And indeed it does. It drops off steeply, but eventually it'll hit values close to negative infinity. So I know, well, let's start with domain. And remember, brackets or parentheses for negative infinity because we never achieve it. And then as I sweep across the graph, clearly there are x values chosen because I've gotten y values out, all the way until I get to this spot here. So this would be 1, 2, 3. So at x equals 3, something happens. Now, my big question is, was I allowed to choose a value at x or not? And since I have a solid dot, I know that I have an output at x equals 3, so I'm going to use a bracket. So that's the domain. Then what was the range that was the result of choosing those domain values? Well, again, starting at the bottom using sweeping motions or sweeping method, I see that this side, the left-hand side of the graph, goes down to negative infinity. So again, negative infinity, and then the highest point or the highest y value I achieve has these double peaks here. So that would be at y equals 1, 2. And my question is, did I achieve 2 or did I just skirt close to it and not actually get there? But indeed I did get to 2. So I'm going to close the bracket. This time we want to use the graph to find the y-intercept. And after we've done that, we want to go ahead and prove it algebraically. So the y-intercept is the place where a graph crosses the y-axis. I am going to identify it as likely to be this lattice point here. Let me get a color we can see. Right there, this lattice point. So my estimation is that the y-intercept is at y equals 4. Now remember, finding this algebraically, there are two ways. There's the actual algebraic way and then there's the shortcut method. So I'm going to show you the actual algebraic method first to remind us what we've done in the past. So if f of x equals x squared minus 4x plus 4. So if we've identified that y equals 4 as the y-intercept, what we've actually noticed is that the point, if I were to label this as an ordered pair, that the point is at x equals 0, y equals 4. And we're going to take advantage of the fact that x equals 0 to find the y-intercept, because x equals 0 at every y-intercept, that's the x value. So let's just plug 0 in for x, and again I'm going to kind of use a modified version of the big gaping hole just to be careful. So 0 squared is 0, minus 4 times 0 is 0, plus 4, so the f of 0 is at 4. So I've not only identified using the graph, but I've also proven algebraically that the y-intercept is at 4. Alright, so same instruction, only this time we're looking for the zeros, and we will confirm them algebraically. So if I use the picture, it appears that I have a 0 at 0. So x equals 0. I have another 0 at negative 1. And I have another 0 at 1. Okay, so let's use algebra to determine if that's true. F of x equals x cubed minus x. So remember, finding zeros is about not setting x equal to 0 inside here, but setting the entire function value equal to 0. So if I let f of x equal 0 and factor, I should be able to find the zeros I'm expecting. So first ME, then mother's face, then chicken feet. So x equals minus 1 equals 0 whenever x equals 1. And x equals plus 1 would be 0 whenever x equals negative 1. And so indeed, I have gotten 0, 1, and negative 1 for my zeros. So now a brand new concept. We're going to look at symmetry. We may have talked about symmetry casually in Algebra 2, but for pre-calc we want to formalize the whole idea. So if you look here at this parabola, you can see very clearly that it is symmetrical around or about the y-axis, meaning if I were to take this sheet of paper and fold it right on the y-axis, the right-hand arm of the parabola would fold over and lay straight on top of the left-hand arm. And so this graph is symmetrical with respect to the y-axis. So we say symmetrical, but we don't spell it that way. With respect to the y-axis. Okay, I took a shortcut there. That would be the lettering for with respect to the y-axis that I would use, and if you used that I would know exactly what you had done. But we want to formalize this idea, so not just be able to see in a picture clearly this is symmetrical, but what does it mean to be symmetrical? So let's label a few points to kind of get hold of that. If I look here at the point, what is that, 1 for the x-axis, let's get a better color here. So right here, I'm going to label this point 1 for the x-axis, and it's at 1, 2, 3 on the y-axis. If I look straight across to the point of symmetry, on the other side, what is the coordinate for that point? Well, now I'm at negative 1 on the x-axis and 3 on the y-axis. So I have the coordinate, for the coordinate, the y-axis remains the same when I'm symmetrical with respect to the y-axis. The y-ordinate remains the same, but the x-ordinate changes. Let's just confirm it real quick with another point. Let's choose this point, so we know that the ordinate for x is 2, and the ordinate for y is 1, 2, 3, 4, 5, 6. And then straight across to the other side, the point that's symmetrical across the y-axis, my x value changes, so I'm at negative 2, but my y-ordinate stays exactly the same. So symmetrical with respect to the y-axis means that the y-ordinate remains the same for the opposite x-ordinate. So the opposite of 1 is negative 1, the opposite of negative 1 is 1, y stays the same. The opposite of 2 is negative 2, the opposite of negative 2 is 2, y stays the same. On a table that looks like if 1 directs to 3, then the opposite of 1 would have to also direct to 3. And if 2 directs us to 6, then the opposite of 2 would have to direct us to 6. And in fact it does. And if you plug these values into the function, you would see that's true. 1 squared is 1 plus 2 is 3. Negative 1 squared is positive 1 plus 2 equals 3. So pictorially, logically, and in a table. All right, so let's look at another, and sorry for all the bouncing around. For some reason when I paste all these pictures in, everything bounces around. It's hard to get back to where I was. So so now we want to look at symmetry another way. If you look at this picture, clearly it is not symmetrical with respect to the y-axis, and I can show that by picking any point. Let's pick, well, of course there are no lattice points to pick. All right, so let's pick this point here. Looks like it's at 3, negative 1. That means at -3, -1, I should have a point for y-axis symmetry, and I don't. Or, we haven't talked about it, but it should be kind of clear and obvious that if I have the point where the x stays the same, but, excuse me, yes, the x stays the same, but I get the opposite of y, I should have symmetry about the x-axis. So I should expect to see a point over here for x-axis symmetry, and I don't. So I don't have any kind of obvious symmetry, but you should recognize another kind of symmetry that we've worked with a lot, which is across the line y equals x. Right? So when we worked with inverses, we got this symmetry that a point that was on one part of the graph was symmetrical by switching the value of x and y. So if I call this x is 3 and y is -1, then on the other side I should just get a reversal, -1 and 3. And I do right there. So this is another kind of symmetry. It's the same sort of symmetry that we looked at when we were dealing with inverses, but we call this symmetrical with respect to the origin. With respect to the origin. So of course the origin is the center, right? The 0, 0 point on the graph. And if you imagined I were to stick a pin right here where my dot is, my orange dot is, and just rotate the paper clockwise or counterclockwise, either way, oh, that's the same direction, counterclockwise or clockwise, that I'd be able to take this arm and just rotate it right around and it would lay straight on top of this arm. So symmetry with respect to the origin is a rotational symmetry. And I have sort of shown this graphically or on a table, but let's go ahead and put in a couple of values just to show what that looks like. So again, when I looked at x equals 3, I'm going to have to flip my colors back and forth. X equals 3, then y was -1. So then I want to look instead on the other side to see if whenever x equals -1, does y equal 3? And that's a question mark at this point. So I look over here at x equals -1, cruise up here, and indeed I get the opposite, or the switching of my x input and my y output. And I can look at another point real quick just to make it as clear as possible. So let's look here at x equals 1 and y equals, oh wait, yeah, x equals 1 and sorry, got a little hung up. X equals 1, y equals -4. So if this is symmetrical about the origin, then I should get -4 and 1 is a point on the other graph. So let's have a peek over here. I should get -4 should give me 1, and it does. So that's a picture, an image where you imagine rotating the graph backward or clockwise or counterclockwise to get the same one arm laying on top of the other, or you can see on the table x values and y values switch. That's origin or symmetrical with respect to the origin. All right, so let's take it just a step farther. I'm going to come back up here to the symmetry with respect to the y-axis, and we want to look at this a little bit more. So a definition: when a graph is symmetrical with respect to the y-axis, we call that an even function. So this is an even function. And when we refer to even functions, we have a little bit of algebra that we can do on this, because while it's convenient to be able to look at a picture, we're not always going to want to graph the graph in order to figure out whether a function is even. And while it's convenient to create a table, we all hate making tables, so let's try to move into some algebra to identify whether functions are even or odd. As you can imagine, there must be an odd function. So let's look at the algebra for this. I know that the function value is y equals, excuse me, let's change it to function notation. F of x equals x squared plus 2, and I'm certainly allowed to do that because they gave me an equation, a y equals equation, and I've confirmed that this is, in my mind, that this is indeed a function. It's going to pass the vertical line test, so I'm allowed to switch the notation to function notation. And then I want to do a little bit of work with that function. So if, kind of painted myself into a circle here, let's see if I can move this around a bit. I guess I painted myself into a box more than anything. All right, so a function is even if the f of minus x equals the f of x. What the hey? Well, that sort of makes sense because we already talked about if I take the opposite of x, then the function of the opposite of x should equal the function of x, logically. But let's look at it in the function. So that means I'm saying, if I take my function and I put in f of negative x instead of f of x, then what do I get out of it? So I have negative x squared plus 2. So you can see all I've done is I've taken my function, used big gaping hole algorithm, and plugged my negative x inside. Well, what happens to negative x when I square it? Well, the negative 1 and negative 1 is positive, so I get x squared plus 2. By plugging in or substituting negative x into my function and then simplifying, I just got right back to my initial function. So if that happens, if I plug in negative x and it takes me right back to the original function, then I know I have an even function. So let's see what happens with the symmetry if I plug in negative x. So again, they've given me an equation at this point. I'm going to solve it for y. So y equals negative 6 over x. And then I can confirm pictorially that this is indeed a function. It has asymptotes, but I don't care about that. It does pass the vertical line test, so I'm going to change my notation to the f of x equals negative 6 over x. Now I want to plug in negative x. So what happens if I put in the f of negative x equals negative 6 over negative x? Okay, because all I did was plug in, by explicitly write out big gaping hole algorithm. Now simplify, well, 2 negatives makes a positive, so the f of negative x equals 6 over x. And notice that that is not, right? That is not the same thing. Let me write not the same thing. Not even. So not even. And I want to clarify that because notice what it is. Let's go back to this sort of funny notation. What happened when I did plug in f of negative x? I put in the f of negative x, and what I got out was I got f of x back, right? Because I got 6 over x, except I got the opposite of 6 over x. So when I put in a negative x into the original function, when I switched out for a negative x, what happened is it took a function that was negative. I got exactly the same thing back, except it was negative. I got the opposite of the original. And when this happens, this is an odd function. Odd function. So even functions are functions that are symmetrical with respect to the y-axis. Odd functions are functions that are symmetrical with respect to the origin. And what happens with a graph that is symmetrical, or a function that is symmetrical with the x-axis? Well, let's take a quick peek real quick. It's a little redundant, but let's do it quickly. So suppose I have this graph. to be symmetrical with respect to the x-axis, I would have to have the reflection over here. And what do we immediately notice? It does not pass the vertical line test, so it's not even a function. So there is no function for whenever a graph reflects over the x-axis. It's an equation. It's a perfectly great graph. You've sort of seen these graphs before, right? Can't this one be that, a hyperbola? But it's not a function, so we are not going to deal with it at this point.